Okay, so I forgot to hit record until partway through. So this is section 2.0. This is the beginning of unit 2, really important unit. So the I can statement, or our objective for today, is I can understand parent functions. So write the word parent right here. Parent functions, and we want to be able to draw them quickly and accurately. So the first question is, these should look a little bit familiar. So if we take a look through here, this one should be recognizable. This is called a piecewise function. And there are lots of different types of shapes that we can have there. And it's a good name because it does come in pieces. Doesn't always have 3 pieces. This one happens to have 3 pieces. This next one is a linear function. Happens to be y equals x. And we can remember some of the key points that we use. We use 0, 0, 1, 1, and negative 1, negative 1. So if we were to label those, it would look like this. So 0, 0, and then 1, 1. Sorry, negative 1, negative 1. Does that look right? Negative 1 comma negative 1, and there we go. And then this is an exponential, so I'm just going to write expo right here. And then remember, any exponential has this type of shape right here. It's got these 3 key points, negative 1, 0, and a 1. This is always a 1 because any number to the 0 power is 1. And then this is going to be the reciprocal. And let's say, for example, that this is 2 to the x. So that would make this 1 over 2, because the negative in the exponent means reciprocal. 2 to the negative 1 would be 1 over 2. And then 2 to the first, that would be 2. So this point right here is 0, 1. This point right here would be 1, comma 2. And this point right here, part way up, so this is going to be negative 1, comma 1 half. And then you'll remember, this has an asymptote of y equals 0. It kind of comes out here and levels off there. So the important thing to remember about these is these functions make shapes. So that's kind of the big idea. Functions make shapes when we graph them. Okay, and I would much rather work with a picture than I would with a description or an algebraic expression or something like that. And we also need to remember about function notation. So function notation is this f of x thing, and f of x is the same as y. And I kind of like this in this order. Some people write y equals f of x. And I like this order right here better because f of x equals y. We plug in an x and we get out a y. It's right in order of the ordered pair. So we plug in an x, we get out a y. We plug in an x, we get out an f of x. Okay, so the most basic shape that we're going to come across for any particular one is called a parent graph. And if that shape is common enough, then we give it a special name so we can refer to it. So we've got linear graphs here, piecewise, we've got exponential. We're going to talk about a whole bunch of parent graphs in this unit, and this is the most important one that we're really going to cover all year. It's called a quadratic, and it's this shape right here. It's f of x equals x squared. If you wanted to, you could write y equals x squared, and we're going to do this by graphing 5 key points. So I've already picked the x's, so what we're going to do is we're going to plug each one of these into the function. So this is going to be a negative 2 squared, a negative 1 squared, a 0 squared, a 1 squared, and a 2 squared. So if we square each one of these, when you square a number, it's always going to turn out to be positive. So if I square 0, I get 0. Well, at least it's not negative anyway. Square 1, I get 1. Square 2, I get 4. If I square negative 1, I end up with positive 1. And if I square negative 2, I end up with positive 4. So what we're going to do is we're going to graph this shape right here. And this shape has a special name. So the function is called a quadratic, but the shape is called a parabola. So it's called a parabola. And then the center point is called a vertex. And that vertex is at the origin, it's at 0, 0. So we're going to go ahead and graph this right here. So we're going to graph 0, 0, and then 1, 1, and then 2, 4. Got to go up a little bit further. And then back 1, up 1 squared, back 1, up 2 squared. And then this is the shape right here. And the pattern that we can use is right here. So we start at the origin, start graphing at the origin, right here. And then from the vertex, and this is the key idea, from the vertex, we're going to go right 1 and up 1 squared. So right 1 and up 1 squared. Then from the vertex again, we're going to go right 2 and up 2 squared. So that would be up 4. And then we do the same thing on the left. Okay, that should be about where I left off. Hopefully there's no repeat, but then we'll be spending some time thinking about this and how these parent functions work. Okay, so this is called a parabola, and I probably ought to write this so we can actually tell what I'm saying. Parabola. Okay, the central point on a parabola is called the vertex, and on the parent graph, it's at the origin, so it's at 0, 0. So here's what we're going to do. We're going to graph the vertex at the origin. We're going to graph it at 0, 0. And from the vertex, we're going to do this. We're going to go right 1, and we're going to go up 1 squared. So write the word squared right here. Then again, from the vertex, we're going to go right 2, and then we're going to go up 2 squared. So if I go to the right 2 and I go up 2 squared, what's 2 squared? 4. And then I can repeat the pattern on the left side. So from the vertex, I'm going to go left 1. I'm going to go up 1 squared. I'm going to go left 2, and I'm going to go up 2 squared. Yeah.
For that one, you only went right 1 instead of 2.
Right here.
No, the third one.
Okay, take a look. Okay, watch. Everybody agree that's the vertex? Okay. If I go right 1 from the vertex and I go up 1 squared, everybody agree the point is 1, 1? Matches up with over here. From the vertex, so notice what the list says, from the vertex. I'm going to go right 2, and then I'm going to go up 2 squared, so that's going to be 4. Okay. For this one right here, again, from the vertex, we're going to repeat the pattern on the other side. We're going to go left 1, up 1 squared. We're going to go left 2 and up 2 squared, and we're all set to go. This is the shape. So to draw this, it's pretty steep. It kind of flattens off. And it's not a V shape in the middle. It kind of rounds off like this. So that's the parent graph of a parabola. Okay, real quick. What if I went from the vertex? What if I went right 3? How far would I go up? D? I'd go up 9 because that would be 3 squared. What if from the vertex I went left 3? I'd go up 9. Okay? So why is the pattern the same on the left as it is the right? Why do I get the same 4, 1, 0, 0, 1, 4? Lizzie? Yeah, because when you multiply a negative times a negative, you're going to get a positive. Okay? So negative times negative is a positive. Or I'm just going to write negative squared equals a positive. Okay? That's why we're going up on both sides. And then you'll notice, you don't have to draw this, but there's an axis of symmetry because the left side is the same as the right side. We get an axis of symmetry at x equals 0. This is symmetric right down the center, and the center on this one happens to be the y-axis. Everybody good there? Okay, we're going to come back to that. I appreciate Angela asking the question about like how I was counting. Again, it's from the vertex. Right 1 up 1 squared, right 2 up 2 squared. From the vertex again, go left 1, up 1 squared. We're going up because when we square, it always ends up being positive. Everybody good there? Okay, so here's the next one. This is absolute value. Okay, anybody remember what absolute value means? Sai? Distance from 0, and distance is always positive, so that means the answers are always going to be positive. So take a look at this. If I plug in a negative 2 and I take the absolute value, I get 2. If I take the absolute value of negative 1, I get 1. Absolute value of 0, 0, and this is 1, whoops, and that's a 2. So let's graph these. Negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. So what we get here is we get a shape like this. Now, if you want to convince yourself, you could grab a couple of other points. You could plug in a 3. Absolute value of 3 is 3. Plug in a negative 4. Absolute value of negative 4 would be 4. We'd have this point up here and that point over there. Okay, this is very typical of absolute value graphs. So when you get a V shape on a graph, it's very typical of absolute value graphs. Anybody want to take a guess at what we call that central point right there? Mason?
Vertex.
We do. We call it a vertex. Okay, when it comes to a corner, we usually call that a vertex. And part of this graph looks like the parent graph of the linear function. So I'm going to change colors. You don't have to write this unless you want to. If this was y equals x, it would have this little piece down here. Why is that piece swung up on the top there? -1, -2, -3. Why are they up there? Samara?
Absolute value can't be negative.
Yeah, absolute value can't be negative. So basically it takes the same graph, sometimes we call it the identity function, and we swing each one of those points up there, and that's why it looks like that, okay? We only get positive values out of absolute value, okay? Only positive values. Now we're going to clean that up just a little bit. Did I mention that your only homework tonight is thinking about this stuff? Did I mention that?
Thank you,
Okay.
Mr. Laws.
Oh, there we go.
Thank you, Mr. Laws.
All right. So if you flip the page over, that you've got to get good at this. For almost this entire course, the parent function and the function that we're going to focus on is the parent graph of a quadratic. So if I say we're going to graph a quadratic or I say we're going to graph a parabola, those are both the same thing. So quadratic is kind of the name of the function. Parabola is the name of the shape. So we're going to do this using 5 key points. So do not look at the other side. Here's what we're going to do. The vertex is at the origin. Put a dot right there. And then again, from the vertex for both of these, the pattern always starts from the vertex. We're going to go right 1, up 1 squared. Right 2, up 2 squared. We always start from the vertex, so we're going to come back here and we go left 1, up 1 squared. Left 2, up 2 squared, and this is what it looks like. Now, if we were doing this on a test and we wanted to make sure that we got this right, we'd want to label these. This is 2, 4. This is 1, 1. This is 0, 0. -1, 1, and -2, 4. And if we wanted to get really fancy, we could say x equals 0 is the axis of symmetry. Okay, so if I gave you a blank piece of graph paper right now and I said, hey, can you draw me the parent graph of a parabola? Could you follow that pattern? Can you lock that away? Because we're going to be taking that graph and we're going to be making a bunch of changes to it, okay? This is the most important shape and function we're going to study this year, okay? Comes up all over the place. That rocket that's sitting on the launch pad may be moving back toward the assembly building. Depends on this equation and equations like it. Okay, so here's my question for you. Why does it go up on both sides? Why do parabolas and absolute value graphs go up on both sides? I've got most of the answer right there. You could fill in the blank. Yeah.
When it's squared, it can't be negative.
When it's squared, it can't be negative. Okay, we only get positive values. And I like the way that Samara said that. What she said is it can't be negative. So it could be 0. We do actually get 1 0 out of both of those because 0 squared is 0 and the absolute value of 0 is 0. Everything else we get positive. So the way we say that sometimes is the answers have to be non-negative. None of them can be below the x-axis. At the very least, they can be on the x-axis. Everybody good? Okay. All right. Can I get a thumbs up, sideways, or down? How are you feeling about this stuff right now? Go ahead. Thumbs up, sideways, down. All right, we'll get there. Remember, we get to think about this overnight. Okay, the next one we're going to graph is we're going to graph a square root. So we've talked about square roots. We're going to do cube roots next. They actually have a shape when we graph those. So here's the shape. If you plug a 0 into this, what's the square root of 0? 0. What's the square root of 1? 1. Square root of 4? 2. Square root of 9? 3. Now, a couple quick things. I skipped 2 and 3. Why did I skip 2 and 3? Luke?
Because they've got weird irrational numbers.
They've got weird irrational numbers. They're really ugly. There's nothing wrong with them, but they're not very fun to graph. Okay? -4. Square root of -4? Careful. Can you take the square root of a negative? You can't. This is going to be imaginary, and here's the problem with imaginary. We're going to talk more about these later. We talked about this in the number sets last week. Here's the problem with this. This is a real number plane. Real numbers in the x direction, real numbers in the y direction, so you can't take the square root of a negative number and get a real number. You can't graph that on this plane, okay? So you can put imaginary. We could put NA for not applicable here. So here's the shape. 0, 0, 1, 1. Skip all the way over to 4. And the next one would be 9, 3. And 9, 3 would be somewhere in this neighborhood right here. So if I were to graph it, it would look something like this. Comes in here and looks about like that. No problem with that being off the page. We'd have to have a really wide graph in order to work that. So that's why we're just going to go with these 3 key points. 0, 0, 1, 1, and 4, 2. So 0, 0, 1, 1, and 4, 2. Why are 0, 1, 4, and 9 such nice numbers? On this particular one, maybe not on another graph, but on this particular one, they're pretty good. Mason? Perfect. We're going to say it this way. They're perfect squares. Perfect squares. Why does the graph not exist to the left of the origin? So once we get here, we just have to flat stop. We don't get any points over there. We kind of talked about this a second ago. Why don't we get any points over there? Lizzie?
You can't take negatives and square roots.
Yep, and not get a real number, okay? So we're going to put not real numbers, okay? And I'm going to do this. So I'm going to write the word real. I'm just going to put a square root with a negative and just put a slash through it. That's one of the domain issues that we were made aware of over the last couple of years. Now, if you take a good look, tilt your head to the side a little bit to the right. If you look really closely, doesn't that look like the top half of a parabola? In fact, look at the numbers. 2, 4, 4, 2, 1, 1, 1, 1. Okay, these aren't that impressive, but the 4, 2 should be kind of. And same with the 3, 9 and the 9, 3. So why isn't there a bottom half to that parabola? Keely? Not that it wouldn't be a real number. We're close. Luke?
It wouldn't be a function.
It wouldn't be a function. It would not be a function. So remember, there was this interesting thing about functions that you couldn't have 2 points stacked on top of each other. That was not allowed. 2 points on top of each other is not okay. It's got to pass the vertical line test. And take a look up here. If I had the bottom half of a parabola, a vertical line would hit it twice. If somebody said, hey, what's f of 4? You'd have to say, well, do you want the top piece or you want the bottom piece? We don't like ambiguity. We don't like confusing things like that in math. Okay? All right, let's slide down here. This one's also interesting. You'll notice that we're going to do 5 key points for this. This is a cube root, and I made the graph bigger. So I want you to stop and think for just a second. There's some extra spaces on that. We'll do the first 3, and then I want you to think about what we're going to plug in with. Cube root of 0? 0. Cube root of 1? 1. Stop and think for just a second. What's the cube root of negative 1? You need a group of 3. You need a group of 3 what? Brittany? It is negative 1. Okay, so far I've got these points right here. That is not very impressive. That looks like a line to me. Okay, let's do this one right here. What point do you want to plug in for this one? And I want you to stop and think. We don't want ugly points. We want nice points. So what's the next point we could plug in? What's the next positive value where we could get a nice answer out of a cube root function? D?
8 and negative 8.
Yeah, 8 is going to work just fine because the cube root of 8 is 2 and the cube root of negative 8 is negative 2. Whoops, negative 8, negative 2. So here we go. This should look a little more impressive. Over 8 from the origin and up 2, back 8 from the origin and down 2. So here's what this looks like. This graph does exist on the left side of the origin. Why does it exist on the left side of the origin? The other one didn't. The one right above doesn't. So square root? Nope, just stops right there at 0. Why does the cube root keep going off in that direction? Dane.
Because we times 2 make it on this in the row, and you still get a
Yeah,
negative.
you can get cube roots of negatives. So up here where we said you can't take the square root of a negative, cube roots of negatives exist. So I'm going to write cube root of a negative. Cube root of a negative exists. Okay, and you'll notice that the parent graph has rotational symmetry. So if we were to take this, it doesn't have reflective symmetry. There's no line of symmetry. But if we take this whole thing and we spin it around the origin, okay, it's got rotational symmetry about the origin. Mason, you got a question?
Well, it kind of looks, the cube root of x graph kind of looks like a rotated version of x cubed.
Ooh, it does, if you know what x cubed looks like. You've been playing around with that Inspire calculator too much? Yes, that's a yes. Okay, the last two that we want to look at, okay, again, we're talking about parent functions. If you want to flip the page over really quickly, the rest of this is, and we're going to do these together, so don't freak out. The rest of this is just using these. We're going to graph these over and over and over again, so we're going to get really good at these. These are like flashcards for parent functions, okay? So the last two are this. One of them is a horizontal line, one is a vertical line. So if you see y equals a number, raise your hand if you know for absolute fact, horizontal or vertical. Y equals a number, absolute fact, horizontal or vertical. Gavin. He's right, it's horizontal. That means the other one is vertical. So if we say y equals 2, this is the way I keep them straight. Y equals 2 tells us which axis it crosses. It crosses the y-axis at 2. It doesn't cross the other axis, so that would be y equals 2. X equals -3 would cross the x-axis. It tells us which axis it crosses. Crosses at -3, so this would be x equals -3. Why would we not be worrying about this one right here if we're talking about functions? Why would we not care about x equals a number? Yeah.
Well, because it's not a function, because it doesn't pass a straight line test.
Very good.
And the whole thing's
Vertical
on
line test. Yep. Itself is a vertical line, so it doesn't pass the vertical line test. X equals a number is not a function. It is an important parent graph type of thing. It's just not a function. Okay? All right. Everybody flip the page over. Okay. Take a little breather for a second. Were those shapes that bad? Could you spend a little bit of time tonight thinking about why each shape makes the shape that it does? Why is the square root graph, why is it the top half of a sideways parabola? Why does a parabola go up on each side? Why does absolute value go up on each side? Why is absolute value straight and x squared is curved? If you spend a little bit of time thinking about those, especially that pattern of graphing a parabola, that's all we're after. Okay? All right. So I'm going to go up to the bell today. I'm going to get as much done on this as I can today. We're going to pick up tomorrow. Your homework tonight is to think about the problems that we've done. So at least pull it out, glance through everything that we've done today. You don't have to write anything down unless you want to. I just want you thinking. Is that a deal? Okay. All right. So last year in Unit 6, to be exact, you talked about translations, reflections, and dilations. Okay. We kind of renamed them shifts and flips and stretches and shrinks. Okay. So if I take a function, a parent function, and I add or subtract k, that is a vertical shift. We're just going to slide it up or down. If I change it inside with the x, okay, that is actually a horizontal change. And then you've got to remember something about this. It's a horizontal shift, but horizontal changes occur inside the parentheses, so make sure you keep a track of that. And then this thing right here. Horizontal changes do the exact opposite of what you'd think. So if you think it moves it to the right, it's actually going to move it to the left. If you think it moves it to the left, it's actually going to move it to the right. And then the last type we're going to worry about is, what if we take the function values and we multiply it by something? That's going to stretch it, shrink it, or flip it, depending on the size and the sign. The size is going to be the stretch or the shrink. The sign is going to tell us if it flips, and if it's negative, it's going to flip it from being positive to negative or negative to positive, which is going to make it the opposite sign. Okay? All right, you ready? Okay, here we go then. That's the parent graph. I'm going to give you a 20-second head start. Go ahead and graph and label the 5 key points there. Make it look nice. Okay, I'm hoping that's enough time. Parent graph, nothing weird about this. Vertex of the origin, right 1 up 1 squared, right 2 up 2 squared. Left 1 up 1 squared, left 2 up 2 squared. If I needed to, I could go right 3 and up 3 squared. That would put me about right here. Do you see how it all kind of falls in line with this nice curving shape? That's called a parabola. We're going to graph this. Ooh, that's really good. I like that one. This is 2, 4, 1, 1, 0, 0, negative 1, 1, and negative 2, 4. Okay, any questions? Okay, I'm not going to ask you to raise your hand, but I'm going to ask you to kind of like in your head, raise your hand. Can you do that? Do you feel pretty confident? Okay, if you're not confident in that, we just need to practice. This is easy to do. Might just take a little bit of practice. Okay, I'm going to slide this over here and we're going to take a look at this. What does that plus 3 do to that graph? Exact same graph, we just need to do a plus 3. What does that do to the graph? Wilson?
Raises at 3.
Which way?
Up.
Up. Just right up 3. So watch, here's what we're going to do. Don't do this point by point. You can if you want. I'm going to take that center point and I'm going to move it up 3. Did we change the shape at all? No, so watch. Watch. From the vertex, right 1 up 1 squared, right 2 up 2 squared, left 1 up 1 squared, left 2 up 2 squared. Draw those guys right here, and I will let you get away with this. Label 3 points. 0, 3, 1, 4, right? And I'm going to come over here. This would be negative 2 comma. Let's see, if I went up 4 from 3, I'd be up at 7. Now, if you want to count and you want to take those and you want to move them all up that far, they'll arrive at exactly the same place. Any questions? Okay. Andy, what does this do?
It lowers it by 1.
Lowers it by 1. So I'm going to write down 1. We're just going to describe what happens here. We go down 1. So don't do every point. Take the vertex, and we're going to slide it down 1. It's going to be right here. The shape is still exactly the same. It's still that parent graph. Right 1 up 1 squared, right 2 up 2 squared. Left 1 up 1 squared, left 2 up 2 squared, so up 4. And this is what the shape looks like. Okay, label 3 points on that. Okay, I think you're working ahead. You're working ahead, aren't you?
I would never.
Okay, take a look. I need your eyes up here. Eyes up here. Is that the same point as if I had taken that one and just shifted it down 1? Because it only changes the y coordinate, right? Okay, now, we're perfect timing. I like how this is going. Let's do the next one, and I need somebody to tell me what does that do. Colson.
Move to left 2.
Very good. Left 2. So we're going to take that vertex and we're going to go left 2. And instead of going back and grabbing every one of those points and moving them left 2, we're just going to say, well, I know the pattern. We just moved it over. So from the vertex, right 1, up 1 squared. Right 2, up 2 squared. Left 1 from the vertex, up 1 squared. Left 2, up 2 squared. We good? Okay. Jack, what does this one do?
Moves it right 4.
Right 4. Okay. Yeah.
Aren't you at the square for 2?
Oh,
Like
why
11.
don't we
Yeah.
square this? Okay. If you were to square the entire thing, you could write it as a big long polynomial. Okay. It's harder to graph in that form. So we'll call this a graph-friendly form. This is actually called vertex form. It's kind of like y equals mx plus b. If it's got that quantity and it's squared, you know it's the same shape. It just moved it to the left 2 units. Okay. All right, we'll do more tomorrow. Okay. What's your homework tonight? Think about what?
Stuff and things.
Everything from here backwards. If you want to look at the ones ahead, that's fine. Tomorrow we're going to finish the bottom of this page and the back of this page with different graphs. That's it. Just think about this, and then I'll show you what we're doing in 2.1 tomorrow. If you have any questions, please come see me. If you're nervous about something, if you're scared about your grade or anything like that, come see me. I want to make you feel better. Thank you very much. Have a great day.
You just said you changed my test to 91.
I did say that, didn't I?
Yeah.